John Moore come on the stage. He's a distinguished staff software engineer at Stripe with an illustrious career that includes leadership and roles in engineering, architecture, and research. John is passionate about distributed system and fault tolerance, so why don't you give him a round of applause, big applause to get John onto the stage. Come on, you gotta give me more. From back there, from the bean bags, I see you. All right. Welcome, John.
Okay, thanks, Jose. Thanks, everybody. I am very excited to be here. And I'll be more excited if the slides actually show up. So in the meantime, I'm going to tell you two secrets. So the first secret is that I really like fault tolerance. So when you run the load test and you validate it, OK, my service can do this many transactions per second and get this latency, I'm the guy that turns the load up to see how the service falls over so that I can make it not fall over that way again. The second secret I want to let you in on is that I really like learning about things from new perspectives. And so I'm actually very grateful to be here today because while I'm excited to give this talk, it also means I got to attend this great conference and learn about how we can use patterns from evolutionary biology for cybersecurity, like we heard from Kelly Shortridge yesterday, or what the psychology of estimation is, as we heard from Joseph Pelryan. So I'm going to hope to do those two things for you today, where we're going to learn something maybe about fault tolerance from maybe a slightly different perspective than we usually think about it. And so let's get started. So first question, maybe we click. OK, clicking the button works. All right. Does anybody recognize this? If you recognize this, please shout out what you think it is. Voyager. OK. So this is a picture of the Voyager deep space probe. There were two that were launched. They were launched in 1977. Okay, I am not going to ask how many people were actually alive in 1977. I think, from my perspective, that will actually be a depressingly small number of hands. But anyway, they were originally designed to operate for 5 years. Okay, and they are both still in operation almost 50 years later. This blows my mind that a system like this could be put together and operate in the face of all kinds of different things, right? And actually, both Voyager 1 and Voyager 2 within the last year have been in the news a little bit, and because they ran into some problems. We're actually going to talk about that in a little bit. But the space industry is really interesting because fault tolerance is such a big concern for them. Because nobody is going out to open the hatch on Voyager at this point to make a service call to it. They have to be very careful not to create a 100 million euro brick flying through outer space, right? So fault tolerance is a really primary concern for the design of these systems, probably more so than in the types of software that you and I write. But I think this makes for an interesting perspective because they have focused at such an extreme edge of fault tolerance that they have thought very deeply about it. And so I think it brings an interesting perspective to us. And so what I actually want to do for the rest of the talk is I want to talk a little bit about my favorite paper. This is actually my favorite paper. This QR code is actually a link to the paper itself. It is not even a computer science paper. It was published at an astronautical society, right? These are the people that make and design spacecraft. But this is my favorite paper because it actually distills a bunch of experience in building very fault-tolerant software. GN&C here stands for guidance, navigation, and control. Right? So this is the software that actually controls spacecraft like the Voyager probes. And so it's very dense with information, and so that's why I love reading it, because every time I read it, and I read it every couple of years, I get something new out of it. So I'm not going to go into full detail, but what I want to do is talk about 4 main principles that are presented in this paper, and then relate it back to the types of software that we typically build, hopefully using some more familiar examples. Although I don't know, like how many people work on deep space probes? Okay, I didn't see any hands. So, okay, so good. So this is definitely going to be a new perspective for folks. All right, so Before we do that, we're going to have to start and just do some quick definitions. So the first thing we're going to talk about are states in a system. And my favorite analogy for this is to think about a game of chess. You do not have to know how to learn, or you don't have to know how to play chess to follow along. So don't worry, I'm not going to ask you to checkmate anybody during the course of the talk. But we can think about the state of a chess game basically as which pieces are in which squares, right? And for those of you who do play chess, yes, it's not quite everything I have to know. I'm still allowed to castle and things like that, right? But for the most part, it's just capturing, you can actually record the state of a chess game, right? And then we can understand that that's what was going on at that point. So those are states. Next, we want to talk about behaviors, okay? So this is a knight. And so all the pieces in chess have specific rules about how they're allowed to move. So in the case of a knight, knights are allowed to jump in this sort of funky pattern, right? So this knight can actually land in any of the red squares here, right? And so there are rules that actually say how you move from one state to another, right? And so we're going to call those behaviors. And then there are models. So models are a way of I guess, putting constraints on the state of the system. So models talk about what states are possible or allowed. So in this case, I have shown a state of a chessboard that you cannot actually get to during a legal game of chess. But there's actually a number of problems here. So white has too many kings. The black player has not enough kings. And there is a pawn on the very first row of the chessboard, which you can't have, right? So this is an example of you could actually think of a model for chess as what configurations of a chessboard are actually possible to get into. And the stress here is going to be on possible, and we'll get to that a little bit later. Okay, the other thing that models have, right, models also incorporate behavior. And so if I know what state I am, I know what behaviors are possible, this is what enables planning. So in the case of chess, it turns out that if the white player has two bishops and they're on different colored squares and their king, and their opponent just has a king, it is possible for white to force a checkmate and win the game. I do not know how to do that, just for the record, but I believe that is a correct statement. So that's how models work. And so what we're now going to start talking about is a basic control loop. Right? So we have some system that is the control system. It has a set of objectives. Right? In the case of chess, this is I want to get my opponent into checkmate and capture their king and win the game. There is the system that's under control, which is the sort of overall chess game, if you will. We're going to make observations about the current state. And then the control system has to have a model. Right? They have to understand that, okay, if I'm in this state, there are a series of behaviors that I can take, you can think of these as commands, that will change the state. And because of my model, and I can look at the state, and I can hopefully move the system into a state that's more like what I want. Okay? And so the idea is that I keep going round and round with this, and there's a whole branch of science called control theory that's all about how to do this. So let's get back to the papers. So the paper's main point is that they describe a concept of transparency. And so I like to think of this like transparent like a window, meaning it's very clear what is going on. And so I think explicit could be sort of another synonym here that we could talk about. And the paper really says there are 4 things that you want to be transparent in order to build a really fault-tolerant system. So the first one is we want transparent objectives, transparent models, transparent knowledge. This is knowledge about the state of the system, and then transparent control. And we're going to talk about what all these things mean, and then give some examples for them. So let's start with transparent objectives. Here's the quote from the paper. Real transparency, therefore, amounts to a sort of contract between the issuer of the objectives and the control system achieving them, where success or failure is mutually obvious. I think it's actually this last statement that becomes very, very interesting. So I know that, contract-driven development, right? This is a API contracts. We've heard of things like this. So this notion of contract may be a little familiar to us. What I think is really interesting is this idea that success or failure is mutually obvious, because that is the thing that we're shooting for. So let's look at a couple of examples here. So let's start with DNS. So I can, on my laptop, issue a dig command to resolve a host name. And I'll get an answer back. It says, OK, it's at 10.11.12.13. One of the things that comes back is a time to live. Right? In this case, this says this answer is good for the next 41 seconds. And so if I were to issue the same command again, then the DNS client, which is usually my operating system, but not always, will say, hey, I've actually got a cached answer. Here you go. It's the same answer that it was 1 second ago. But now here's the question. What happens after 41 seconds? OK, so the DNS protocol, right, I have a client. It has a stale cache. Right? It knew at one point, when I looked up example.com, that the answer was 10.11.12.13. But now it's been more than 41 seconds, so the cache is stale. Okay, so it says, all right, sounds good. What am I supposed to do? I'm supposed to go look it up again from the DNS server. So I go and make my request to look that up again. But now I have a network error, or the DNS server times out. Okay, so now what? Now, the DNS protocol, right, like the now what is you get an error. Okay, but I actually think there's maybe a missing interface here, because I can imagine that there are scenarios where even though this cache entry is stale and I wasn't able to look it up again, I might be OK getting the stale response. So for example, if I'm in a service that's making API calls to another service inside my architecture, and I've already got 6 connections open to it, and I'm opening a new one, and I have to do a DNS lookup to go look it up, I'm probably OK assuming that it's the same IP address that I just looked up a couple of seconds ago when I opened the last connection. Not always, right? If I'm talking to somebody else, right, some other organization's API, I might want to be a lot more conservative. But the point here is, the answer kind of depends on my situation, what I'm doing. And so I actually think that there's a missing objective here. And just to illustrate this a little further, I think HTTP caching is a better example of the type of transparent objectives that we're talking about. So how many people have seen the cache control header on HTTP? Anybody? All right, so several people are familiar with this. So when I issue an HTTP request, I can provide cache control directives. For example, I can say, no cache. That means if my request somewhere along the way encounters a cache, I do not want a cached response. I want you to go all the way to the origin server and then come back with a fresh response. Or I can say, I want a response. You can give me a cache response. This is the max age directive, as long as it's no older than this amount. Okay, so as a client, I can start to specify a little bit more about what I'm looking for from the cache. But wait, there's more. So the HTTP protocol actually specifies several other directives. I think these are used a lot less frequently, but I think they're interesting illustrations of the types of expressiveness that we can have in HTTP. So I can talk about we talked about stale responses, right? I can actually be very explicit about I'm OK with stale responses as long as they are no more stale than this amount of time. That can be very useful. Or min fresh, right? So when I get a cache entry, there's a certain amount of time that it's going to be valid, right? The remaining valid time, that's the freshness time, right? So I can say I want you to give me a response that's going to be good for at least this amount of time, right? And there's even one which is only if cached, meaning if you can't give me a cached response, I want you to give me a 504 error instead of talking to the origin, right? And so these are all just ways of being a little more explicit about what success or failure means in terms of serving that request. So I actually think it'd be interesting. I couldn't find any IETF standardization around sort of deadlines, right? Like, what if there was a header where you could say, please give me an answer within this many milliseconds? Would we do something different? Like maybe I would just say, you've asked for the impossible. I am not going to be able to generate a response for you that fast. I might as well just give you an error right off the top, rather than trying to do work that you are going to time out and never receive anyway, right? So I think this type of thing is very interesting, and we don't often build these into our interfaces. So the way that we really think about objectives in this case is that they are constraints on behavior. So in the case of an HTTP cache, I've got the headers that the server sent when it generated the original response. I've got the headers that the client is sending as it's coming to make a subsequent request. There are protocol defaults. So for example, by default, you cannot cache the result of a post request. But if the server says you can, then you can, right? So all of these things together, these put constraints on the behavior of the cache, right? And so the thing that we're looking for is, have I provided enough ways to be very clear about all of the things that I care about from you when I ask you to do something, right? The worst thing in the world is if I say, please do this for me, and you come back and give me an answer, and you're like, yeah, sounds good, I succeeded. And then I'm like, that is not at all what I wanted, right? So here is my first sort of pro tip. So the first pro tip that I have is if I have a situation in an implementation where I am asking myself, okay, I'm in this situation, what should I do? Okay, if the answer is, it depends on what the caller is trying to do or my client is trying to do, then you might have hidden or implicit objectives, right? Because if you don't know what the right thing to do is, because the client hasn't actually told you what they want, right? If they had told you enough about what they were trying to do, you would know what the right thing to do is, right? And so this may be a hint that you don't have fully transparent objectives. All right, so those are objectives. The next thing that we want to work on are transparent models. Remember, models describe what states are possible and what behaviors are allowed here. So models provide expectations against which evidence of state can be compared. Okay, how many people are scratching their heads at this? I scratched my head several times. It's like, what do they mean here? And so I believe what is meant here is that a model just says, if the system is in state X, and then I do Y, I should end up in state Z, right? That's all it's saying. And then if I go look, right, I did Y, and now, wait a minute, I ended up in Q. Okay, this is different from my expectation, right? So now I can try to figure out, is there something else? Something else is going on. I need to do something different, right? So this is really the best way, I think, to think about models. And in order to make them, and I think part of this is when we build software, we often divide the world into normal behavior and abnormal behavior, right? We've got the happy path, and then we've got the error handling path, okay? Transparent models say that this is not the right way to think about things, because there is no such thing as normal behavior and abnormal behavior, or normal states and abnormal states. There's just behavior, okay? And this is, when we start to think about things this way, this is where we get a lot of robustness. So one of the things, I mentioned that the Voyager deep space probes each ran into different types of problems. So sometime last year, I think it was Voyager 2, ended up, it has a radio antenna, right? So it can receive commands from Earth and transmit data back. But its antenna got pointed away from Earth. Now, very ingenious NASA engineers, they did something, I heard it described as a shout. I am not a radio engineer, so I don't actually know how this worked, but they sort of like did this massive broadcast, and they actually got the probe to hear it, and they got it pointed in the right direction. But here is the cool thing. It turns out that if that didn't work, a month later, an automated, basically a cron job, would have woken up, it would have looked around at the stars and said, huh, I'm not pointed back at Earth. I should point myself back at Earth. And it would have actually repointed itself. I mean, you would have lost a month's worth of whatever it was in the middle of doing, but it would have worked. And it blows my mind that they thought of that 50 plus years ago, right, when they were putting it together. And part of that is, if you think about describing the state of the probe, one of the things you could describe is its orientation with respect to Earth, right? And so, you could be a little too simple, right? You could just have this be a bit, right? Am I pointed at Earth or not? Okay, that's okay, but if the answer is not, okay, now what, right? But on the other hand, if I actually describe it as the full, like, and I don't know how to do space coordinates or anything like that, but like whatever, the XYZ orientation of the probe with respect to Earth, if that's how I described how it was working, now it's in a situation where it could actually figure out what it needs to do to get pointed back, right? And so this is where these sort of very explicit, fully transparent models come into play. So let's put things in a more familiar context. So let's say we have a service and it's talking to a database, okay? Database starts generating errors as we send it requests, okay? One way of dealing with this is that, okay, what are we going to do? Well, the service can generate logs and metrics, and some operator can see, oh my gosh, look at all these error messages coming through the logs, or the error rates are going up in my metrics system, and they can say, huh, it looks like the database is down, right? That's actually a model of the database that lives in somebody's head, which I think is really interesting. And so then, okay, we can do something about that. Maybe I've got a feature flag, right? Maybe talking to this database is an optional feature where I can gracefully degrade by turning it off, right? So I can flip the feature flag and stop talking to the database and experiencing all these errors. So let's get a little more interesting, right? So what if there was some kind of model of the database inside the service? And I think a very familiar example of this is a circuit breaker. How many people are familiar with the circuit breaker pattern? So a number of folks, but not everybody. So I'll explain how this works. It is like a circuit breaker in the electric system of your house. And so what it is doing is that as errors are coming back from the database, if you get enough errors, the circuit breaker trips. Right? It says, wait a minute, too much stuff going on. Just like the circuit breaker in your house, if you have a massive surge of current, it will turn it off so you don't start a fire in your house, for example. And then what it does is when the circuit breaker is tripped, it prevents you from talking to the database for a certain period of time, right? So this is a fast fail. This has the same effect as turning off the feature flag, although it's automated. And it relies on a model of the database in the service. Now, the model is not very interesting, right? It is really just, is the database up or down, right? This is one of those one-bit models, right? But it's still useful, right? Because I can actually get better behavior if my service has a model of its dependency. But wait, there's more. Okay, so that's a very simple model. But what could we do that's maybe a little more interesting? Suppose that instead of the database returning errors, suppose it just gets slow. Anyone who was at Aaron Reinhardt's talk from earlier today, he talked about latency injection and sort of gray failures, right? So if the database gets slow, the circuit breaker is not going to help us, right? The database is still up, okay? So now we need something maybe with a little more power. How many people have heard of Little's Law? Okay, a small number of hands. I am very excited. I have a small side story. So I love Little's Law. In fact, how many people have heard of Moore's Law? Right? Okay, so my last name is Moore. Former colleagues said they coined Moore's second law, which says if John Moore has an opportunity to apply Little's Law, he will. So if you want to know more about this, you can come and ask me about Little's Law. But here's the cool thing. Little's Law is queuing theory. All right, I'm going to give you a little basic on Little's Law. When you learn this, you know queuing theory, and when you're having drinks around beers and you're getting into some kind of technical discussion, you can just say, well, queuing theory says blah, 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 and no one will argue with you because queuing theory sounds so intimidating. But this is so simple. It is just n equals x times r. It is no more complicated than that. There is no calculus. It is pure arithmetic. And this is a relationship between n is the average number of requests that are currently being processed in the system. The way I can think about it is these are requests that are sitting in my system in some state, intermediate state of being processed. X is my transaction rate, right? This is the rate at which requests are, but the average rate, I should say these are averages, it's important. But the average rate at which requests are showing up, and then R is the average response time. And the cool thing about Little's Law is it applies to any request processing system. And it applies to any subsystem that is also a request processing system. This makes it super powerful. I have actually debugged performance bottlenecks with Little's Law and pencil and paper and interviewing an engineer that was working on the service. So like that is actually possible. All right, so what can we do here? So let's say we're cruising along. We're getting 2,000 requests per second from the database, and the average response time has been 10 milliseconds. Okay, but now we're seeing elevated latency. Now the average response time is 20 milliseconds. Okay? Little's Law says I should expect that I can only get 1,000 requests per second of throughput. I'm going to assume the capacity hasn't changed, and so if I double R in the equation, then I have to divide x by 2, right, in order to balance it out. And so that's what this is saying. So now I have a model that lets me do some prediction. This is kind of cool. And so now, what we do with this information, well, that depends. Because what does this mean for me? Maybe, you know what, I really needed that 2,000 requests per second. And so now I have to decide, maybe I have to prioritize which requests I'm sending to the database. I have to do load shedding, right, and just do the more valuable ones. But maybe this means nothing to me, because I actually only need 100 requests per second, and it's okay if it takes 100 milliseconds, right? This may literally mean nothing to me, but it all depends. But it's the power of this model where we can look at information about what's going on and then make predictions, right? Remember, we said the idea was with the models is, right, if I'm in X and then I do Y, then I should be in Z, right? So there's a level of prediction that comes with it. And so I think this is a really interesting concept for us to think about, is some more transparent models. Now, there's obviously a spectrum, right? We can start from like very oversimplified models, which are maybe not useful. Although we gave an example, the circuit breaker, like that's about as simple as a model as I can think of. It's got a state of 1 bit. I mean, the real ones have a little more, but it's basically 1 bit. But that's still useful. But then we can come all the way over and think about like a full fidelity model, right? I could be modeling the cache on the database server and like how much memory it has and how many threads it has and what its CPU average and, and how many servers are in the database cluster and, is it running Paxos and like, just like I could fully model it, right? And be really accurate. Now, that is probably a maintenance nightmare, right? Because anytime they change the database, I'm gonna have to change my model. Right? So we probably don't want to do that. If I'm building a full fidelity model, I'm basically implementing a database. And that's what the database is for, not my model. So we really want to find something that's sort of in a sweet spot in the middle, which is we want the model to be interesting enough to be useful, but simple enough that we can create and maintain it. And I would say Little's Law is a good example of this, right? The model is not very complicated. It is n equals x times r, right? There is a very simple arithmetic, very easy to implement, but it actually gives us some predictive power that gets really interesting, especially because for many of us, what we work on are request processing systems. So I think this is something interesting for us to think about. So my pro tip for models is to ask yourself the following questions, which is, do I have a model of my own capabilities, right? I'm writing a surface. Can I describe what capabilities it currently has? Do I have a model in my service of my dependencies, right? That might just be some kind of, Little's Law model. It might be a circuit breaker, it might be something else. But do I have a model somewhere that describes my dependencies? And then here's the kicker, right? Can I adjust the model of my own capabilities on the basis of the capabilities or the current status of my dependencies? This is where the magic comes, okay? I would say this is not common, right? Like I don't think we do a lot of this as an industry. We'll see a little bit more about this as we go. Okay, we're on, that's 2 out of 4, we're on the third one, transparent knowledge. So for transparency of knowledge then, and I have to say like maybe the reason that I read this paper every 2 years is like, okay, it's like very dense text, right? And it's like, okay, what do they really mean? I have to parse it. But anyway, I want to make knowledge explicit. I want to represent it clearly with timeliness and uncertainty, and strive for a single source of truth. Okay? So let's walk through some of these things with examples. So let's talk about uncertainty. All right. I recently ran this command on my laptop. This is the SNTP command. And so it exercises the network time protocol, right, NTP. And this is talking to a time server, NTP server, maintained by the US government. And so for this test, I'm over here at the red X on the right-hand side in Philadelphia, and the server was over here in Denver at the left-hand red X. It was about 2,000 miles, or was that 3,200 kilometers, something like that? I hope I did that right. You know, Americans with their strange units of measurement. But anyway, so this is the answer that I got back. And so I had to look up what this meant. So like, I'm going to interpret it for you. So what this said is, we think the clock at the time server is 47 milliseconds ahead of your clock, plus or minus 63 milliseconds, this is fantastic, right? Because it's like the plus or minus, this is doing a lot of work here, right? Because like what this is really saying is like, well, we think it's 47 milliseconds ahead, but it might actually be behind. We actually don't know which one is ahead. This is interesting. You know, I think for a lot of us, when we think about computers, we think about, you know, especially computers doing arithmetic, we think about exact answers. What's different about a spacecraft, right, a deep space probe, is they have all kinds of scientific instruments on board, right? And so I don't know if you remember back to, you know, when you were in school and learning about science, right? Like instruments, you get a reading, and then it's like there's a tolerance, right, plus or minus whatever. And so this is not something we think about a lot in a lot of our software. But, and in fact, we actually saw this earlier in the talk yesterday about the psychology of estimation, right? The speaker made the assertion that estimates should really be thought of as ranges, right? It's a probability distribution over something, right? So it's an answer plus or minus. So that's really what uncertainty about is, like, what's the plus or minus in what you're talking about. Even if I've gone and queried something, right, and actually this gets to the next point, timeliness, right? If I make an HTTP request and I get a cached response back, one of the things that it tells me is how old is that cached response. There's an age header. In this case, it says, we actually talked to the server 95,000 seconds ago. Okay, which is, what is that, several days, right? I don't know, I can't do math in my head that fast. But anyway, I can see how time in the data is, right? And this is the thing, like as soon as you've got a database separate from your service, you are in distributed systems world, right? So whatever information you just asked the database about may be already out of date by the time that you got it. And so this notion of timeliness is, I think, really important. And then striving for a single source of truth, right? If I have circuit breakers, you know, in all of my services, well, that's not a single source of truth, right? Like I have 3 different opinions about what the state of the database is. And in fact, in lots of cases, the only single source of truth is the observability system, right? This is where actually all of the logs and metrics arrive, and there's one place I can go look to see what is currently going on here. So these are all, I think, things for us to think about. And so here's the next pro tip, which is, remember, we want to have models of our dependencies. So for each one of those, do I have one place to go for its current state? Is that current state been annotated with sort of its freshness and accuracy? Right? So an example of this might be like, let's say that I have a configuration server somewhere, and every 10 minutes, I'm going to go look up what my current configuration should be. Right? And then I'm just going to hold that in memory, and when I want to know what the configuration is, I just ask the in-memory sort of thing. So if we had freshness on it, I would say we might do something different. Right? If I am expecting that I'm polling it every 10 minutes, and then I look, and it's like, I got this a minute ago. All right, sounds good, I'll use that. But what if I looked and it said, wait a minute, it's been 1 week. since I actually talked to the configuration server, I might do something different, right? I might, at the very least, put my hand up and say, someone needs to come and look at me because this is not behaving as I expect. Remember, we're talking about expectations of things, and that's what the models give us. And then finally, if I've got a model, do I have some way to keep my information up to date? Right? In the case of a circuit breaker, for a database I'm talking to all the time, I can just kind of observe it as it happens, right? I can say like, well, how fast was that query? How fast was that query? How fast was that query? Oh, that one was an error, right? I can just observe it as it goes, and I can build up some notion of like, should I trip the circuit breaker? But if I'm not actively talking to the database, then I might need to supplement it, right? I might need to send the equivalent of like a ping query, right? Like select one, right, from the database. And like, did I get a response back? Yeah, okay, database is still there. That looks good. So, and in fact, I might need both of these. And I think this is what's interesting, is like we don't often think about the fact that I might need both, right? Because there may be weird states that I could get into, right? I'm expecting to talk to the database all the time, but what if I don't? Right? Now I need something else, right? And so this is where thinking through possible states gets to be very powerful as we go. All right, real quick, we're going to do transparent control. And here the principle is that if I understand the behavior of what's possible, I understand my objectives, and I understand what state I'm currently in, then no other information should be required in order to make a control decision. And so really, what this is saying is that when I'm making a control decision, it is a function from my current state and my current objectives to a set of actions. Now, where's the model, right? That's one of the things we talk about. The model is in the implementation of this function, right? And so what is really cool about this is that this is a stateless function. Now, you're like, John, literally one of the parameters is named state. And so no, this is a stateless function because we've actually made the state explicit and we've passed it in. And what's really cool about this is that makes it possible to test this, right? And in particular, if we look at the way we represent the state, it encourages us to be more thorough about exploring the different situations we might be in, right? If the data type that I have for expressing the state, right, can, in the case of the deep space probe, if it includes like my full which way am I pointing in space with respect to the Earth, I might be encouraged to think about, well, what do I do in certain of those sorts of situations? And so these are places where maybe things like generative testing, could be useful. If you don't, that's property-based testing. Some folks, anybody use Quick Check or things like that? That's basically what it is. You can ask me about that later. Or you can just look it up on Wikipedia. But the idea is to you just generate test cases at random to explore more of the state space as you go. So let's put it all together. Okay, this is another place where I am from the US and we use weird units of measurement. So this is a picture of a thermometer that uses degrees Fahrenheit. So 62 degrees Fahrenheit is actually quite pleasant. 62 degrees Celsius, that's like being in a sauna. So just wanted to call that out. This is not from the inside of a sauna. This is probably inside just a regular house or something. But this has all of the things that we've talked about. There are objectives, right? It says, aha, remember we said objectives are constraints on behavior, right? So it says, hey, I am in heat mode, right? And I'm not in air conditioning mode or cooling mode, right? I have a target temperature. I'm allowing the thermostat to control the fan, right, for moving the air around. And there's this thing called permanent hold, which basically, if you haven't, this is like if I've got a schedule for like how I want the temperature to go, this suspends the temperature, right? And so those are all constraints on the behavior as we go in here. There's obviously state, right? What temperature is it actually in the room? There's a model in here, and that at the very least, in the case of a thermostat, says if it is too cold, run the furnace or whatever the heating element is. Now, it turns out they're actually, like, even not smart thermostats like this have a little bit more sophisticated of a model because they're careful about you don't want to run generally heating elements intermittently. It's more efficient if you sort of wait for the temperature to drop a few degrees and then you run it continuously to bring it up. And so they have models for like how to do that properly and things like that. And then there's actions, right? Like, am I actually running the heating element to heat things up? So this is control loop in action, right? This is this stuff in a very familiar setting for us. But okay, what about microservices? Because we are not running a bunch of thermostats, right, in our production systems. So in the remaining time, I want to try to pull this together and talk about what I think we could build together using these principles as an industry. And so let's set things up again. We've got a number of services that are talking to a database here. They probably each have connection pools, right, for talking to the database, a certain number of connections they'll keep open. They might be in an auto-scaling group, right, where we're growing and shrinking the number of instances as we go. And we're generating metrics, right, telemetry and logs and so on, coming from the services, coming from the infrastructure platform. And, at least we have like some operators that are looking at the observability platform, right? And so, and they're in charge of configuring stuff, right? So their job is what's going on, what do we want to do, and then, or what do we want to have happen, and then what should we do as a result? Which, if you have been paying attention, is the type of control loop thing that we have been talking about, except it's just happening in people's heads. So what if we were to make it a little more explicit? And we built a microservice control plane. And so we just make all those elements explicit in here. So it would obviously need to have objectives, right? I need to tell the control plane, what are you trying to do? It's going to need to have a model of the system, right? It's probably going to need to know like some concept of what's going on with the dependencies, what's going on, how many service instances do I have, things of that sort. It can subscribe to the same metrics that we were already using, right? That's okay. It'll probably have a model. Maybe it has this Little's Law model in it, right, to figure out what we want to do here. And then it can actually do the configuration, right? It can change the auto-scaling parameters. It could change the size of the connection pools and things of that sort. What is really cool about this is if we've followed all these transparency principles, is that this can be a stateless service. The microservice control plane itself can be stateless, because it can just observe the state from the telemetry system, right? It's got its baked-in model, right? And so as soon as it's gathered enough information about what's going on, it can begin making control decisions and configuring things for us. And so if I lose it, I just spin up another one, right? This could just be a singleton instance in a Kubernetes pod, for example, right? I can just replace it, and there's no state to retain because it's inherently stateless. And that also, as we said before, means that we can test it. What is it going to do in various scenarios? And so the neat thing is that we can still have our operators, right? And they can still issue objectives, except now they're issuing it to the control plane instead of directly configuring things themselves. And so the key thing is that if the objectives are transparent in the way that we've described, where success, right, success and failure should be mutually obvious, then this becomes a tool that augments the operators, right? Because they can express the objectives and understand the objectives, right? Those should be things that make sense to them, right? I can use a thermostat because I can set a target temperature, right? I don't necessarily need to know, like, well, how many degrees is it going to wait before it turns it on? No, I just like, please make it be 62 degrees. And then it will take care of the rest. And so I think this actually gets very powerful. And so let's talk a little bit about the objectives. If folks are familiar with service level objectives, right, and service level agreements, right, these talk about things like what throughput is supported, concurrent request rates, latency profiles, right? What's my median latency supposed to be? What's my 99th percentile latency supposed to be? Is there a maximum error rate? Things of this sort, right? This is how we talk about these types of agreements and objectives. Usually service level objectives are self-imposed, right? This is what I believe the system should be able to do or what I've designed it to be able to do. And then our SLAs are for our clients, right? These are the promises that we make to others. And so the way I think about it, and generally, right, the service level objectives should be tougher than the service level agreements, or we're going to be doing a lot of apologizing to our clients, right? So what I think this means is we should think about the service level objectives, these are the capabilities of my service, right? This is what I'm currently capable of. And the SLAs are really a good way of describing the objectives that we want the service to be able to obtain. And so we can also, if we have these control planes, we can actually put them together, right? So if I have service A that calls service B, they can each have their own control plane, and those control planes can communicate, right? So the control plane can say, like, here is actually the type of service that I want you to be able to provide to me, right? Sort of making a reservation for a certain amount of throughput or a certain latency profile or something like that. And then the control plane for B can respond and say, like, here's the things that I can currently do. If I'm degraded, right, I can't support that other feature, I can advertise that so that people stop asking me to do that for a certain period of time. And so they can make their own adaptations, right? But I can also confirm those reservations as I go. And so we can also put this together, right? If I have some other service that also calls B, it can actually do the same thing. And now the control plane for B is the place where this can all come together, right? I can actually look at the collective set of objectives that I'm required to sort of meet and figure out what to do, how to resolve any conflicts that are in there. Because I actually have a single place where that can happen now, which I think gets very interesting. The other thing that this gets us is a little more predictability, right? So auto-scaling, right, this is something that is an adaptive mechanism, right? We're going to scale up and down according to its own model. You can also make connection pool sizing adaptive in a very similar fashion based on errors from the database or timeouts or things of that sort. So the question is, if I have both of these adaptations going, like, what is going to happen? How do they interact, right? They're usually implemented completely separate from one another. And so we get a little less predictability out of this. So when we see a spike in latency at the database, okay, so which of the following things should we do? Should we add more instances of the service? Should we adjust the connection pool sizes of each of the service instances to the database? Should we adjust the thread pool sizes in the main service threads of the services? Should we do all of those things? Or should we do nothing? Right? Like we said before, sometimes I don't need to do anything, right? Because I have these multiple mechanisms that are adapting on their own, I don't have a way to figure out which of these things to do. And so that control plane gives us a place to figure out what we want to do in these situations, because we actually have modeled that fully, or at least to the degree that we want to build a detailed enough model to figure out what's going on. So that's what I've got for us today. So in summary, this paper, which I do encourage you to read, it's a super cool paper, because it's about space, right? And space is cool. But if we can get transparency of these four things, right? The objectives that I'm trying to meet as a system, my model of how the system behaves and what the possible states are, right? Not just what the desired states are, but what the possible states are. Transparent knowledge about the state of the system, and then transparent control decisions, right, which we've all described here. I think we can build service control planes that are robust, right, because they include models that can consider, like, all possible states. They're more robust, just like the Deep Space Probe, because it knew which, it could model all possible orientations with respect to Earth. It's in a position to be able to actually point its antenna back to Earth, right? They're coherent. We have that one place to be making these decisions about what mechanisms we want to be putting together. I've shown how these can be composable. But more importantly, I think especially if we model these things as SLAs, right, and capabilities, they're actually understandable, right? And so I think this is the key thing, that when we have automation, right, the difference between something that augments the humans that are using it or not is really to the degree to which, like, when I ask you to do it, like, how well do I understand, like, what you're going to do? Maybe not how you do it, but, like, what you're going to do, right? Can I actually express what I want you to do? And so I think this way of thinking about things gives us tools like this that we can access programmatically, right? We could write things that ask the control planes to do things automatically for us, right? Especially if we have the composition that I talked about here. But we still have our human operators that can make use of them too. And so this is why I love this paper, because it's got all of these great ideas. Obviously, they've had a ton of success in building fault-tolerant stuff. If I write software that is still running somehow 50 years after I wrote it, like that's amazing. I can't even imagine that, right? Now, I don't think we have to go quite that far, but I think this way of thinking about things means that, with just a little bit, right, we can increase transparency in just one of these things at a time, and it will help, is I think the point. And so I'll leave that to you. Thank you very much for the time here today. And that's what I got. So ready for questions.